on HTM-based update-side synchronization for RCU on NUMA systems. Disclaimer: this work was done prior to the first author joining Amazon. The views expressed herein are those of the author. Read copy update is a synchronization mechanism for read master workloads providing almost ideal performance and scalability for reads. However, the RCU users should synchronize concurrent updates by themselves. This is intended to allow users selecting or implementing best synchronization mechanism for them. However, many users use the global locking, which is a simple but imposed scalability problem. To mitigate this problem, many RCU extensions have proposed. In SOSP 15, read log update has proposed. It adopted a software transitional memory-like logging mechanism for updates. And in Pact 17, RCU HTM has proposed. It encapsulated each update in an HTM transaction. Will those scale on NUMA machines? Both RLU and RCU HTM had not evaluated on huge NUMA machine, but with single socket machines utilizing 16 threads and 44 threads respectively. So, we prepared a server utilizing 4 sockets. In each socket, there are 18 physical CPU cores and hyperthread is enabled. So in total, there are 144 hardware threads in the machine. Also, please note that every following evaluation also uses this server. For the evaluation workload, we use random list, insert, and delete to kernel space linked lists, which are protected by RCU, RLU, and RCU HTM respectively. The evaluation results are shown in this slide. As you can show, unexpected poor scalability has revealed. The RLU imposed significant overhead to reach, and with updates, both RLU and RCU HTM degraded the performance as multiple NUMA nodes being started to be used. What are the root cause and implications of the research? The RLU's read overhead apparently comes from the varied version searching. Therefore, read must performance sensitive workloads would not be able to easily use RLU instead of RCU. And the NUMA oblivious designs of RLU and RCU HTM degraded the update scalability. Especially in case of the RCU HTM, the amplification of HTM upwards on NUMA impacted the scalability problem. However, the HTM benefit is clear, so we need NUMA-aware HTM use for read-massive workload. So, we designed a new RCU extension called RCX with our principles. First, do fine-grained update-side synchronization. Second, use pure RCU read mechanism for the ideal read performance and scalability. Third, use HTM. Only HTM provides hardware-oriented high performance. Fourth, access only NUMA local data objects within HTM transaction. Otherwise, abort rates exponentially increase. Finally, isolate the HTM working set from the dominant readers. Otherwise, the readers abort HTM transactions. And this is the interface of the RCX. The readers do nothing special except notifying each start and completion adjacent to that of the RCU. However, in RCX, update critical sections should specify items to update. Except these, others are same to RCU. The quiescent state-based reclamation is used. Let's show detail. In RCX, it embeds node local locks and a global lock to each object. And updaters first acquire the per node local lock using HTM. Once they acquire the local lock, they commit the transaction and acquire the global lock using spin lock in this time. And the updaters who acquired both local and global locks can update the items. And this is the evaluation result of the kernel space linked list protected by the RCU variants, including the RCX. As you can show, the RCX performs best for both read-only and update mixed workload. Similar research have shown with the hash tables. We further applied RCX to Linux kernel virtual memory system and a popular email DBMS called CacheDB. As you can show in this slide, the improvements were significant with these macro benchmarks either. Conclusion: the RCX achieves best update while preserving the almost ideal read in terms of performance and scalability. owing to its NUMA overviews of HTM. And there are many details and additional things in the paper, including the detailed investigations of state-of-the-art, including an HMCS lab and RCX variant, and also optimization of RCX for memory efficiency and HTM implementation details are in there. Finally, the source code is freely available at GitHub. Thank you for listening.